Okay, so let's talk about the optimization function for this particular machine learning algorithm, and we will going to study about the gradient descent, which is the optimization function, and we're going to see how we can use it to optimize the weights and minimize the cost function. So the optimization algorithm is something like this. We derive the cost function with respect to each of the theta values. And whenever we take derivative of any function, what we're trying to do is we're trying to measure the change, the difference in those values. So when we take the derivative, we're actually measuring the difference, the change, and we need to minimize this difference in order to get those optimal values. So when we take the derivative with respect to theta, this gives us another equation which looks like this. And then what we do is we go increase the process and we take learning steps. Each learning step is like a loop. Every loop will be done, and so for the sake of learning, let's imagine we only have one theta. If we have one theta, then we only need to derive the cost function with respect to that. So the equation we will get will look like this one, and there will be no more subscript operators. So this is the only equation we'll get, and the theta will be multiplied by x minus the actual value. So after this, when we see that this will be repeated n number of times, so the n number of time repetition is actually the iteration process which we will take, and through every iteration we will move closer to the minimum value. So the cost function, the mean squared error, is actually a convex function. A convex function shows us that there will always be a global minimum. A global minimum is where the cost is minimum, and at that position the theta values are optimum. So what our purpose over here is that when we initialize the random values of theta in the beginning, they have a higher cost. But as the optimization algorithm proceeds, the cost will reduce and we will move towards the optimal theta values. And with every step, the difference will become more and more less. So at the beginning, the difference and the learning steps, you can say, will be bigger, and as we move towards the global minimum, they will slowly become smaller. So in order to better model this, what we're going to see is another equation. So the first thing we're going to do in the vectorization form, we're going to take all the derivatives. We're going to take all the derivatives of the theta values and we're going to put them in a vector. So with respect to theta 0, with respect to theta 1, and we're going to represent them in the form of vectors. So in the vector form, it becomes rather simple. We have xt, we're going to multiply them with the x theta minus y. So in this way, we have vectorized the derivative of the cost function with respect to each of the theta values. Afterwards, we're going to take the training step, or you can say as the gradient descent step. This is where actually the learning takes place. So theta is actually minimized when we subtract it with the derivative of that particular corresponding theta. So in this way, when we have the vectorization function, we can just take it and do it collectively, and the total number of steps will depend, and that is actually a hyperparameter. The total number of steps will be determined as we will continue to move until there is no more change in the function. There is no further decrease. So this is the learning step. So another parameter over here is what we call n, is the learning rate. Learning rate is another hyperparameter and has a very important function. What learning rate does is that it determines the size of the gradient descent steps. So the big question is, what value should we initialize it with? Whenever we have a hyperparameter in a machine learning problem, this is what we need to decide by following either the conventions or by hit and trial method, or by using a grid search, by using different types of values and see which value is working best for your particular problem. So commonly we have a learning rate between 0.1 and 0.01. So that is by convention and it has worked many times. So the thing you need to measure or take caution over here whenever initializing the learning rate is that if the learning rate is too small, the gradient descent will take very little steps and it will take forever to reach it for the global minimum. So it cannot be too small. But if it's too large, the gradient descent will diverge. If it diverges, it means that it will take huge steps bouncing from one another and it might never reach the global minimum. So you may never get the optimal weights. So another way to do this is by using the normal equation. You see that we do this in n iteration steps, which is another hyperparameter, but you can say that we continue the loop until there is no decrease in cost function. But in order to do it in a much different way, we can use a normal equation. The normal equation, what it does is that we use matrix formulation and matrix operations to directly jump to the optimal value. We take the inverse of x transpose multiplied by x, and then we multiply it by x transpose and actual values. So the normal equation is very good and a good approach when you have limited number of features in a dataset. You can do that. But let's say you're dealing with images and you have thousands or millions of features, then you cannot do that because it will take forever, and it will take forever to multiply, and it might not be so much computationally efficient.